In this video, we are going to see a small introduction about elastic collision of two particles and later on about scattering. Now, at first, elastic collision between two particles. It could be considered as what would happen inside a ideal gas. So, if you want to do a small game molecular dynamics of an ideal gas, you would probably make something where the energy is conserved and they would probably act like rigid spheres. What does elastic collision mean? It means that the internal state of the two particles that do collide doesn't change, and thus you can neglect the internal energy of the two particles. And when you're doing the conservation of energy, you can only consider the kinetic energy of the two particles. And if there is some kind of potential energy, that potential energy. Because of course, if it wasn't completely elastic, there would have been some kind of change inside the structure of one of the two particles, or both, and so you should have considered the internal structure and internal energy of these particles. Now, at first, the easiest way to approach this problem is considering it from a reference system that is posed on the center of mass of the system. So if the system of mass moves, our origin will move, and it will be exactly on the center of mass. And actually in this reference system, you will simply see the two particles arriving and then going back in a very simple way. So they will have two velocities, and for the conservation of energy, the velocities of the two particles will simply be rotated and not change in modulus. So we'll call it C, the reference system of the center of mass. You will simply see the two particles arrive, and then when the collision happened, go back again. So again, we are going again to use the formalism where we consider it like one body. We use a pseudo one body Lagrangian instead of the two body ones. So if we have velocity, that is velocity of particle 1 minus velocity of particle 2, we will call the starting velocities in this reference system like VO1 of the first particle. That will be m2 v m1 plus m2, and then of course we will have VO2, and it will of course be m1 v m1 plus m2. Then after the elastic collision, we will have that V01 first, so after the collision will be M2 V N0 M1 plus M2, and view Z02 first, like M1 V N0 M1 plus M2, and this N0 is the versor. Wait, I forgot something. Yes, okay, here is a minus sign. Forgot the minus sign. Minus VO2 first. Okay, now it's correct. And this N0 is then a new versor, so a module 1 vector that will say the new direction of the velocities, because okay, this very simple situation is where they hit in this way, but if they have some more complicated interaction, they could also go in some other directions, because they may have some different kind of interaction that causes this change in direction. Or they could not hit head first, but they could hit themselves in a not perfectly front way, and so they could have some different velocities. They could go in some different ways, but they will always go into opposite directions. So the velocities will be rotated somehow, but with the same modulus. So this was the easy way, but of course it could have happened in some different ways. And this is the result. But now we would be more interested in what happens in our laboratory frame center of reference system, because this is the center of mass reference system. So in the reference system of the laboratory frame, we have to add the velocity of the center of mass. Thus, we will have that after the collision. In this case, I have removed the O to say that it's the laboratory frame, so laboratory. The velocity will be again n0 m2 v m1 plus m2 plus m1 v v1 plus m2 v2 m1 plus m2. And the same thing, of course, for the second body. So the same thing for the second body. But now, this is the maximum we can get using the conservation of energy. But we don't know anything actually about the direction of this n0. That is actually what we're interested in which direction are our two bodies going. And of course, this can be seen a little bit better in a geometrical way and using momenta, because the things get a bit easier. But of course, you must know the starting conditions. But we will see it now. So, in the laboratory reference system, I pass it to momenta by multiplying by m, m1 and m2, the previous expressions of velocities. As you can see, mu is the reduced mass, for the rest everything is unchanged. Oh yeah, I forgot that actually this part is equal to this vector and this part is equal to this vector. Okay, now geometrically we can see it way better. So if we have this circumference that as a radius has n0v, and we can quite easily try to understand a little bit better the P1 and P2 and actually the angles, because of course we have θ1 and θ2. Yeah, geometrically we can see that correlation between the angles of P1 first and P2 first, and how they will relate, and which are the possible values, because of course they have always to touch C, because they must always have n0v, they must always be n0v plus this part. So they have always to be the sum. And so they can only be on the circumference. So once you know the angle of one, you can actually get the other vector. But of course, if you don't have this kind of starting conditions, if you don't have this kind of formations, it's impossible to know more about it. But in this way, with this graph, you can understand a little bit better what may happen and what may not if you have enough information. And you can actually understand why there is a correlation between the two angles and how you can, and what's the kind of correlations. It's a triangle. But the most interesting situation isn't that in which both the particles were moving in the beginning, but it's actually the situation in which one of the two particles is at rest in the beginning. And this should already remember you something, because we are slowly fading away from elastic collision and going inside scattering, because it's not a straight line. We are going to introduce it slowly. Oh yeah, of course, the bottom vectors depend on the starting values of P1 and P2 of the starting momenta. Thus, using the starting conditions, you can already know at least something. Okay, in the situation in which we have that particle 2 was at rest before the collision, of course it won't be at rest anymore after the collision. We have that the mass of the particle 1, so the one that collides on the still particle, is minor of that of the particle 2. This is how you can describe it. The second vector, this is P1 first and P2 first, so after the collision. B will be on the circumference at this point, and A will be inside. You have theta 1 and theta 2, so the two angles. Here you have again the same N0V, and here you're starting to introduce this key that will actually say how there has been a deviation from the beginning path for the particle you're considering, or better, for the this pseudo single particle inside a central field that we are actually using in order to have a easier Lagrangian. And the interesting thing is that in that case, you can find a correlation between chi and theta 1 and theta 2. Between chi and theta 1, it's this a bit more complicated expression, m2 times sin chi divided m1 plus m2 cosine chi, while theta 2 is 1/2 pi minus chi. And so if you know that one of the particles is at rest, you can already get a lot more information about the system after the collision. In another situation in which m2 is smaller than m1, so if we are interested in m1 bigger than m2, even if actually inside scattering it's usually the opposite, the particle you're throwing on your system is usually smaller than the atoms you're studying. For example, if you throw a photon, so light, it will be much smaller than your particle. Or if you throw some electrons, some protons, they're usually smaller, or some neutrons, they're always smaller than your big nuclei that you are studying. But of course you might be interested in case particle M1 has a bigger mass than M2. In that case, A would be outside. So you would have here theta 1, and you would actually also have a maximum angle. Okay, this is how you would represent it with mass 1 bigger than mass 2. So if I was throwing an atom to an electron, something like that. And in this case, you also have a maximum possible angle for the heavier particle. Okay, now we are seeing scattering. So a situation in which I have one still body as before, and I throw on it a beam of lighter bodies. Again, we are going to consider it in the reference system of the center of mass, and we are going to again consider it like one body in a central field in order to simplify our life. So this is if we have this body that goes in this direction, so we have this infinite velocity from which it comes, we will call it infinite velocity because it would have been, the velocity would have kept forever if there wasn't the other body or the central field. And then it will be deflected because it's of course a repulsive central field. Otherwise it wouldn't be scattering, of course, but it would start rotating around it or something like that. And then it will go away, having a new infinite velocity with the same modulus as before, but a different direction. And A will be the nearest point to the center of the central field. That is this. Now the distance between the center of the central field and our infinite velocity is the impact parameter. And that's a very important thing. And then there will be this angle that will be between the center of our field and the nearest point of the trajectory, and we'll have again key that will be the deflection angle, the angle at which it's deflected, because it would have gone in a straight line, but it won't go in a straight line anymore, and I want to know of how much this angle is, so I know where I will be able to find it with a detector. Because if it goes in this way, I want to know where I have to put a detector in order to find this exact particle. Now, we're going to arrive slowly to what we are really interested in finding. And so, at first we have that we can find phi 0, so this angle, and it's an integral between the minimum distance, so distance of A and infinite, of m divided per 2, so it's actually the formula we have already seen, because it's again the angulus inside a body in a central field, so 2m. So this will be again the formula, but we will rewrite it in a different way using rho, so the impact parameter, and the infinite velocity, or better its modulus, because it will be easier. So again, r min infinity, so rho, so the impact parameter, r squared dr divided 1 minus rho squared divided r squared minus 2u of r divided mass times infinite velocity squared. So I said infinite velocity is the modulus of this velocity. Now, by using this, we can know this angle phi 0, and with this relation, so chi equal the absolute values of pi minus 2 times phi 0, we can know chi. So the angle, the scattering angle, the angle at which our particle will be deflected by the central field. So now in a scattering experiment, we might be interested in knowing which is the probability of finding a particle being deflected in a certain area. Or better, usually we will use some kind of solid angle. So an infinitesimal ring in space in which I want to know which is the probability I will find something if I put a detector. And this will depend, of course, on which area of, if this is the center of our central field, how far away my particle hit. As there is no angular dependence, it's of course always a ring. So of course, if I hit in this area, I expect to arrive here. But the question is, what's the probability? Of course, it depends on the angle. It depends on the distance, and actually this distance and the angle have a 1-to-1 ratio. So you can always find a function to bind them somehow. And yeah, so there are these two quantities, the differential cross section, and then if you integrate on the whole solid angle, the absolute scattering cross section. But we are going to show the differential scattering cross section because it's actually the probability, the interesting thing. Of course, then if you want to know in general what happens, you can integrate it on the whole solid angle. So in general, some other places I've seen it with different notations, but I will use the one that I found in the Landau Lifschitz mechanics book. Of course, this differential cross section will be the number of particles that pass it in this infinitesimal space divided the total number of particles through. So it will be the number of particles that in the end scattered where I expected divided the total number of particles, because of course it must be normalized depending on the number of particles that actually the beam contains. So it can be photons, electrons, as said. You can scatter with almost anything you're interested in. This can then be rewritten on the dependence of chi. So a function of chi. So rho of chi, the rho of chi in the chi, the chi. But actually, it's usually much more interesting in making it in a function of the solid angle and not of chi, because it's actually what you're going to measure and what you're going to see and what makes more sense. And so it transforms in rho of chi divided sin key, the row of key in the key, d, the solid angle. I call it like this. I've seen it also call it in this way, so it really depends. You will see it in many notations. But I will use this small o, small 0. Of course, this is in the reference system of the center of mass. But if then you're interested in having it in the reference system of the laboratory frame, you only have to reuse the old formulas we have already seen to colligate, to pass from key to the theta 1 and theta 2 angles. You remember the one where theta 2 is equal to 1/2 pi minus key, and the tangent of theta 1 is equal, this more complicated expression, m2 sin of key divided m1 plus m2 cosine of key. So this is for a generical situation. But again, we still haven't seen what happens when we do really insert true potential energy inside. So, for example, a rigid sphere, a Coulombian potential, or whatever. Actually, we're going to see rigid sphere, Coulombian potential, and then a small angle scattering, because there are some experiments of small angle scattering. It could be interesting to see what it means. So, the easiest case is that of the sphere, rigid sphere. So, it will go straight on as long as it doesn't touch the rigid sphere, and then it will be deflected somehow. If it's if the impact parameter is 0, it will go back, of course. So it will go forth and back again. If it's not 0, it will be deflected somewhere, as you can see here. The impact parameter can of course be re-expressed in function of the radius a and of the angle. So a sin phi 0 equal a cosine 1/2 key would be this angle here, because it would be the deflection. And so in the reference system of the center of mass, the effective differential scattering cross section can be rewritten as can be written as 1/2 pi a squared sine d key equal 1/4 a squared d. So it can be rewritten as 1/2 pi a squared sin key d key equal 1/4 the square of the radius and the 1/4 the square of the radius and the solid angle. If we want to translate it in the laboratory frame, the formula becomes a bit more complicated. But you should keep remembering this, because it actually will come back. So if the scattering cross-section according to particle 1 will be this incredibly user-friendly formula, and as you see, it's quite complicated. But you might notice one thing. Very often we will throw very light particles on quite heavy ones, and actually the heavy one will very often be fixed inside a position because it's, for example, part of a solid, so it can't move somewhere. This means that usually, for one reason or another, you can say that M1 is much smaller than M2. Thus, M1 divided M2 goes to 0. So, if M1 divided M2 is 0, or goes to 0, this goes away, this disappears, and this disappears. So what remains is 1 divided 1, that is 1, plus 0, so 1. And so what we get in the end will be d sigma 1 is equal to 1/4 a square d 0 1. That is again the simpler formula we had in the reference system of the center of mass. So actually what we can get from this is that very often in our systems, or better in the kind of experiments we do as chemists, we don't need actually to use the more complex laboratory frame formula, but we very often can simply use that of the center of mass. Because there is the thing that if you have a mass from particle 1, the one that you're throwing at the system, very smaller than the mass of particle 2, you can use that simplified formula. In fact, you will very often see this as the formula of the laboratory frame. But usually this is an approximation, so remember it. Now, historically, and very important situation in which scattering has been used has been the Rutherford scattering. In that situation, in which Rutherford understood that the nuclei have a massive, or at least almost the whole mass of the atom inside the nucleus, that this nucleus is much smaller than the complex volume of the atom, and that it's positively charged, has been discovered with the Rutherford scattering. So, what's the formula of the Rutherford scattering? So, in the reference system of the center of mass, it's remembering at first that the potential, the electromagnetic potential, is equal to an alpha that can be a positive or negative number. Thus, we can have attractive or repulsive, so this formula will work in both situations, divided the distance from the charge. So we will have the sigma equal a divided alpha divided 2m u infinity squared dO divided c fourth key half. So in the reference system of the center of mass, so C, this is the formula of the Rutherford scattering. But in the laboratory system, if M1 is much smaller than M2, otherwise the formula would be more complex, we can say that the scattering differential cross-section is, so it's again substantially the same thing, only instead of key I have theta 1. So again, if I use a much smaller particle and I throw it against a much bigger one, or a fixed one, because of course if it can't move, you could consider it as it had a huge mass. At last we are going to very quickly see the scattering differential cross-section in case of a small angle scattering. So a small angle scattering is when the impact parameter is very high, and so there will be only a little deviation, so a small value of key. And so I actually have to move my detector only a little bit from the origin in order to see my particle arriving. I will show it directly in the reference system of the laboratory frame. So it will be d sigma 1 equal to d rho d theta 1 rho of theta 1 divided theta 1, and then of course the solid angle 1. So this is the formula. Now in general, in the majority of our chemical experiments, usually we will always have to deal with the quantum effects. So the systems will be more complicated with more interactions and more complex results. But having seen at least once the classical counterpart will for sure simplify your life in understanding the more complex systems.